Well, what is special about these improper integrals? What's wrong with them? What makes them improper? Well, if you look at this expression here, 1 over the cube root of 7 minus x, it doesn't look like there's anything really particularly wrong with it at all. Except it's 7. When x is 7, won't this be 1 over 0? Won't this be infinity? Right? That's what makes it an improper integral. If you put this fella into the calculator, and in particular, you looked at what was happening round about 7, it would look something like this. For those who've taken Calc 1, can you remember a guy called a vertical asymptote? Big fancy name for it. But what happens is that for this function, and the function I'm talking about is the 1 over the cube root of 7 take away x. As you take values of x closer and closer to 7, this function gets huge. It goes infinite on you, right? It basically does that vertical line thing. And if you wanted to find the integral from 0 to 7, can you see that there is a problem at 7? So that's what improper integrals of type 1 look like. They don't have infinities here or here. That's what the ones last week were like, right? 0, infinity, that kind of thing. And they have a problem at one of the two endpoints, in this case at 7. And so we're going to look at whether or not this integral is equal to a number. And if it is, we will say it converges. And if it is a number, we'll say it converges to whatever that number is, say 7/12. Or it could be infinitely big. And when it's infinitely big, we say that it diverges. And you don't need to say anything else except that. And the technique that we're going to do is very similar to what we did last week. We're going to use limits. So it's going to be the limit as t tends to 7 of the integral from 0 to t, 1 over the cube root of 7 minus x dx. Isn't that very, very similar to what you did last week? Except you'd say the limit is t tends to infinity, right? Because it was an infinite limit. So we're going to calculate this guy. We're going to plug x equals 0 in, x equals t. We're then going to make t become 7. And sometimes the answer is going to be, 4/9, in which case it converges. And sometimes the answer is going to be infinity, in which case it diverges. So first thing I'm going to do about this integral, this guy here, is I'm going to change the way it's written. Instead of 1 over the cube root of 7 minus x, I'm going to call it 7 minus x to the power of -1/3. Are you happy about the -1/3 power and where it came from? Do I need to get into details? Or are you comfortable with a cube root being a -1/3? We're cool, we're good. Now, there are two ways to do this. Do you know I could do a U sub, which I'm not, but I could if I wanted to. And if I was going to do a U sub, it wouldn't be a very awkward one, it would be that. And if you did a U sub, you will get the right answer. And that might be the way that you will tackle it. What I'm going to do instead, because it's much quicker, is I'm just going to look at that and say, well, that's one of those guys that you can use the linear shortcut method on. So it's a power rule. So I'm going to add 1 to the power, divide by the new power. Now, if this x here was 2x, wouldn't I multiply by 1/2? If it was 4x, I'd do times 1/4. Remember the little bit at the end of the linear shortcut method. In this case, it's -1, so I get -1. And this fellow is going to be evaluated at x equals 0 to x equals t. What I'm going to do now is I'm going to rewrite this mess in a way that's going to make it a little bit easier to calculate. So the negative gets me -3/2. No, not with that. Then you have this fella here, 2/3. 2/3. Oh. Could you hold on a second? I have been waiting for this. I apologise. Hello. Yes. If it stops, oh, I used this. All that stuff out. So all do pasta, originally quite different. 10 to 11, 10 to 12, 1 to the I don't know if it helps with your point. I apologise, everyone. You know how life gets in the way, and I needed to do that. I totally apologise. Now I'm going to do something your mum does, right? Do as I say, not as I do. So none of you are allowed to take phone calls while I'm teaching, okay? Yeah, I know it's not fair, but whatever. Here we go. 7 minus x to the 2/3. That's actually the same thing as the cube root of 7 minus x squared. Now, you might think that's a lot of work, but we're going to have to do a limit here. And the worst thing you want to do is to try and calculate limits with fractional powers, because most people don't do it well, right? They just don't know if it's 0 or is it infinity or is it 42 or what. They just can't figure it out. Too much going on. So turn the thing back into the look so it looks like the original. Right. Now I can start putting in the limits of integration. So it's going to be -3/2, the cube root of 7 take away t squared, subtract. If you put 0 in here, you're just going to get the cube root of 7. So it's take away -3/2, the cube root is 7 squared. Are we good so far? Anything not making sense? If it's good, I'll continue. Now, when we did limits when it was infinity, wasn't one of the main techniques brute force, which basically means you just make the t infinite and you see what you get. So let's see what happens when I make t 7. Okay. Would you agree, whoops, forgot my little cube root. Would you agree that 7 take away t becomes 0? Right. If t is 7, 7 take away And you're going to get 0 in these questions. That's what happens. Now, what happens to this 0 is you cube it. Isn't it still 0? Or square it is still 0. The bottom line is, won't this just be 0? All right, this is an ugly mess, but we can fix it. It's positive 3/2, and the cube root of 7 squared is the same thing as the cube root of 49, if you want to make it nicer. And so we can now say what the answer is. This particular one converges, and it converges to that ugly answer. So it's a number. That integral there is the number 3/2, the cube root of 49, whatever that is, it's fine. Okay, that's our first example of an improper integral of type 1. So far, so good? You know, you are allowed to make weird faces if you're not happy. Rena, what you got for me? It looks like you were trying to say something. No? Okay. Rena, you again, were you trying to say something? It goes yellow when people are making a noise. So I don't know whether it's just a noise or you.
I'm fine.
You're fine. Okay.
Yeah.
No with that. Well, the one I just did was question 12. Let me show you what the homework questions look like, and that way we can figure out which ones I need to do, because you might say that one looks weird to me. Okay, so give me a few seconds. I think you are looking at the homework. Are you looking at question 12 here? Nice and big. Can you see question 12 is the one I just did, right?
Yeah.
So your answer would look something like this: convergent, and then you type in that big ugly, what would it look like? It would go 3/2. And then you'd go over here and you do what was that? Square root, cube root, right? I don't know if you can do a cube root with this thing. I think you'd have to do it this way. Yeah. Okay. Well, anyway, you would type it in. I don't want to spend ages playing a bit with that. Okay. Would you agree that 13 has a problem? Which one of those limits, the -2 limit integration or the 14? Where is the problem with question 13?
-2.
Agreed. So if you were doing this question, wouldn't it be the limit as t tends to -2 of t to 14? What would this weird 4th root of x plus 2, what would we rewrite it as so that we could do the integration? Two on the top, 4th root of x plus 2. What fractional power would that become?
-1/2.
If it was a square root, yes. But since it's a 4th root, how would you tweak that negative? There's a tiny little 4, so it makes it not a square root, but a 4th root. -1, -1/4, right? 4th root's -1/4, cube root's -1/3. Do you see the difference? Come back to that one. This one's a little bit different as well. This one's back to the usual. What would this one become?
The -1/3.
Yeah, -1/3. And that's the end of those ones. So do you want me to do another one of those fractional guys, or can we move on to doing a different type of type 1 question, something that's a little bit different algebraically? What do you want?
Something different would be nice.
Okay, let's show you question 15. So I'll write it down. It's the integral from, in my case, 0 to 1. And it's 85 on the top. And it's got the square root of 1 minus x squared below it. And bear with me for a moment. I'll return back to our usual whiteboard. Here we go. Oh, that window that I couldn't find disappeared. Right. Would you agree that the problem here is that x equals 1, not at 0? Right. You look at the guy and you say, okay, which one's causing the trouble? Is it the 0 or is it 1? 0 is no problem, 1 is. So that tells me that I'm going to do this as the limit as t tends to 1 of the integral from 0 to t. And apart from that, you just write everything else down as before. Now, why does this one, is this a bit different from the others? This is not a negative power. You know, you're not going to turn this into 1 minus x squared to a negative a half, because we're not going to do it using the power rule. We are going to do this guy using a fella that you already know about. And I'll bring this fella over to remind you. The 85 isn't the issue. That just means it's 85 something. What is the integral of 1 over the square root of 1 minus x squared?
The inverse.
Yeah, inverse sine. Right, I'm pointing at it. So, yeah. So in this question, we didn't really have to do that much to find the integral. Would you agree it was already pretty much ready to be used? So that's what made it different. Now, it's going to be the limit as t tends to 1. 85 inverse sine of t. Take away 85 inverse sine of 0. And now we will plug in 1.
Are we allowed to take the 85 outside of the parentheses since it's a constant?
I would. I didn't do it, but I should have. Yes.
Okay.
Right. Now, let's do this one. When someone says, well, you're trying to find the inverse sine of 0, you're trying to find what angle is the sine of 0. Can you trust me that the answer to that is 0? What angle gives you an inverse sine of 1? Right, so what you're looking at here is an angle whose sine is 1. What angle has a sine of 1 in the first quadrant?
(90).
Right, and in degrees, he's quite right. It's right there, 90 degrees. But we do radians, so pi upon 2 is what you would say. So 85 pi upon 2 is. So, hey, this thing converges, right? And it converges to that guy. Okay with that question? Did it come through without too much algebra? Let's show you a different version of yet another type 1. How about the integral from 0 to 2 of 1 over x squared? Okay. Where's the problem with 1 over x squared? At 0 or at 1?
Zero.
Now, I tend to put in a lot of lines of working. I'm not suggesting that you need to do exactly everything I'm doing. But one of the reasons I kind of write quickly and put these in is that you can always go back and watch the video and catch a line if you missed it. But if you want to look at it, it kind of shows you everything I'm doing without skipping lines. So have you noticed that the 1 over x squared is now being written as a negative power? You know, just like the 1 over square root situation was. And why am I doing that?
Makes it easier to integrate.
Yeah, because I'm going to use the power rule, which is a very common rule to use in these questions. And you add 1 to the power, and then you divide by the new power, and you will evaluate it from x equals t to 2. But I am not going to leave that guy. I'm going to do some style points on it. You know, the question was a fraction. Try and make your answer look the same. So this is going to be the limit as t tends to 0 of negative 1 over 2, take away negative 1 over t. So that's going to become the limit as t tends to 0 of negative a half plus 1 over t. Okay, time for brute force now. If you make t become closer and closer to 0, aren't you going to have to find 1 over 0? Now, some people, hopefully you're not one of them, think that 1 over 0 is 0, but it's not. Isn't 1 over a tiny, tiny number infinitely big? So 1 over 0 is in fact infinite. And so the answer is that this particular one diverges. So it is possible for type 1 integrals, improper integrals, to have an infinite area, to diverge. Does that seem reasonable that it could happen? Any problems with that question? Okay. So here is another question that looks like the same question. 1 over x squared from negative 1 to 1. And here is the danger. If you do not know that there's a problem at x equals 0, couldn't you just call that x to negative 2, do your usual stuff? And trust me, if you did it, you'd get an answer 2, right? The area of that integral would be 2. But it's not. What you have to do with this question is realize that since the problem is at 0, you have to break the integral into 2 separate pieces. You have to find this guy and you have to find that guy. And then you can figure out whether the answer converges or not. The question that's similar to this one in your homework is number 14. Now, I've already done a kind of version of that one. It's this guy here, only difference is I had 2 there. And can you trust me that the answer here is infinity and it diverges? So this piece is infinite. So here's the logic. Suppose this piece was a number like 42. 42 plus infinity, wouldn't it still be infinitely big so it diverges? So if you're doing one of these questions where you had to split it into 2 pieces, just find one of them. If one of them happens to be infinitely large, it diverges. You do not need to even find the second one. The whole thing is bound to diverge. And so that can save yourself a little bit of work. I say, this is my way of phrasing that, if one bit is broke, the whole thing's broke. Right, so if one bit's divergent, the whole integral is. And it doesn't even matter if that guy is Well, imagine this answer is plus infinity and that answer is minus infinity. They both are diverging. You don't say, oh, well, they add up to 0, because that's not how infinities work. You can't add or subtract infinities. That's not the way they work. Are we cool with that last version? That's the end of type 1. There's not as many, what's the word I'm looking for? It's not that heavy on the algebra. Maybe the cube roots are a little bit messy, but not that bad. So what we're going to look at to finish this section off is we're going to look at what's called the comparison theorem. And we are going to look at the comparison theorem, and we're going to return to type 2 improper integrals, right? The ones with infinity on it. So suppose I had an integral from 1 to infinity. And this integral was 6x over x cubed plus 1 dx. Now, if you try to integrate that, don't even worry about the infinity. If you try to integrate 6x over x cubed plus 1, can you trust me it can't be done? You might say, well, I'll do a u sub of x cubed plus 1. Well, that would be a reasonable approach. It just doesn't work. Can you trust me that there are some integrals we just don't know how to do, right? Nobody's figured out a trick to get the answer, right? So what do you do when you want to know, does this converge to something? Now, you don't care what number it converges to, that's a good thing. But if it does converge, you have to know it. And so you're going to get a whole bunch of questions where there's only 2 circles. One of them is converge. Oh, well, convergent, I guess I'll use their phrase. And the other is divergent. Now, I guess if you're doing the homework, couldn't you pick the first one, and if it told you were wrong, you'd pick the second one and the question would be over. But if you did that, you wouldn't be learning anything, you'd just be guessing and, you know, fixing your answer accordingly. And secondly, if you get a question like this in an exam, final exam in your case, I won't give you any points if you just pick that and don't show me why you picked it. So let's show you how the comparison test works. It's really sneaky and really cool. Since we're only interested in this integral when x is huge, we can do a little bit of what I call surgery. You put a little funny equals that looks like the OC symbol, and what that means is it's approximately the same value. It doesn't mean it's exactly the same value, but it's close to it. This guy is approximately 6x over x cubed. Well, think about it. Would you agree that a billion cubed plus 1 and a billion cubed are pretty much the same in the big scheme of things, right? They're almost the same. And so that is allowed. So if I wanted to find the integral of this fella, this guy would do. In other words, I compare it to something much simpler that I do know how to integrate. Well, you might say, that's ugly. Yeah, that's ugly, but it's not as ugly in a few seconds, because isn't it that guy? Now, when you do the surgery, and we'll do more of these, you only pick the biggest power of x on the top and the biggest power of x in the bottom. So see if the bottom was x cubed plus x squared, it'd still be x cubed in the bottom. See if the top was 6x plus 50, it would still be 6x on the top. Do you understand what I'm saying when you pick the biggest power of x in, right? You don't care about the other bits, just one thing on the top and one thing on the bottom. And the one thing has to be the largest power of x. So this fella can now become the limit as t tends to infinity of the integral from 1 to t. While I'm at that, to save 1 line of working, I will combine a couple because we've done enough of these. And this is going to become the limit as t tends to infinity of, well, add 1 to the power, divide by the new power, evaluated at x equals 1 and t. And what do you how do you think I'm going to rewrite negative 6x to the negative 1. How do you think I'm going to rewrite that?
Just 1 over 6x.
Almost. The over x is right, but the 6 stays put.
Oh, yeah, okay.
Right. And you know the reason I'm doing that is in a few minutes from now, a few seconds from now, isn't that going to become a t? And then that t is going to become infinite, right? And if I say to you 6 over infinity, you're going to say 0. If I say to you negative 6 infinity to the power of negative 1, can you see you're going to have a harder time figuring out what the heck that's going to be? So let's get this bit out of the way first. It's going to be negative 6 over t, take away negative 6 over 1, which is basically that guy. So what have we got? Negative 6 over infinity plus 6. Would you agree negative 6 over infinity is just nothing, 0? Infinitely small. And what you've got is a converges. And it converges to 6. That's your answer. Now, oops, I take that back. I can only say for sure it converges. I cannot say that it's 6. You know, it might actually in real life converge to 5 or 6.12345. We don't care about that because all you do up here is you fill in the dot that says convergent. Right? There's nothing else to be asked. Did that make sense? This comparison test trick. Oh, I got a good thumbs up. I like thumbs ups. So all I'm going to show you for the few minutes that I want to spend on this is, I'm trying to find the damn thing. Oh, there's only 2. Okay, so I guess I'll show you the last one then. I won't do the whole thing because you have to have practice. There's an x plus 1 and there's an x to the 4 minus x. So the bit I'm going to show you is who to compare it against. Okay. For this fraction, who goes on the numerator? Who goes on the top?
X?
Yes. Now, the bottom's going to be a bit weirder. The square root of x to the 4 take away x. Remember, only one thing is allowed on the top, apart from like 5, looking 5x, right? One term on the top, and on the bottom, one term. So this is a bit trickier. Who do you think is going to go in the bottom, the denominator?
X squared?
Whoa, yes. I wasn't expecting that answer, but it's correct. Can you see why she chose x squared? Well, that's the answer I was expecting to hear. Agreed, x to the 4, the biggest power. But isn't the square root of x to the 4 x squared? And now, this fella here, which is the original question that we're trying to find, does this converge or does it not converge? This guy here, he behaves like, well, oh, wait a minute, isn't that just 1 over x? Okay, would you agree that's a much easier guy to do? Agreed? And I believe that one diverges, but you can check it. That's pretty much the end of that section. And actually, that's the end of that particular chapter. So if there's any questions, I'm ready to move on, unless there is questions. Okay. So chapter 8's only got 3 sections in it. Kind of short. Let's look at chapter 8. And in particular, section 8.1, finding arc length. So what we are going to do is basically follow a formula that allows us to find the length of an arc, as it's called. If you bear with me for a few seconds, I'm getting the next section loaded up. But darn it if I can find it when I want to. Damn it, where are you? There you go. Almost done. Right, okay, we are good. Well, let's show you what the problem is. Imagine that you've got a function, f of x, and it starts here, x equals a, and it curves and it finishes up here, x equals b. And we would like to know the arc length. And the arc length is basically the distance that you would travel if you walked along the curve. Right, so you can imagine that you're a little ant and you're walking from here to here. How long is that piece of string? And you are just basically given a formula that allows us to calculate it. And if you look up the textbook, you can actually see a proof of it. And it's called the arc length. And we typically use the letter L. And you get it by, not surprisingly, integrating something. And you integrate from A to B, which kind of makes sense. And then a bit that doesn't quite make sense, but this is what works. The square root of 1 plus the derivative of this guy squared. So it's kind of magic, right? It's a formula I give you, and you can go and check the proof to make sure it works. But essentially, you have to find this guy. Now, heads up warning, your head is going to hurt probably, I don't know, about 20, 30 minutes from now, because these questions start off easy and then they get ugly, and they get ugly really quickly. And that means that you're going to have to deal with some heavy duty algebra. Not so much the integration, although that can be awkward. What's going to be more awkward is you're going to have to deal with really messy algebraic situations, and ones that you're maybe not comfortable with or had a lot of experience with. But by the time this is over with, you will have a lot of experience of it. So hopefully that'll make it better. Now, this version is when you get a function like y equals x cubed, right? But there is a second version of it. So I might as well do it now before we actually start looking at some questions. And we don't do as many of these because they're not as common, but we do sometimes. I want you to imagine a function starts here and it finishes here, and it starts at y equals c and it finishes at y equals d, and we still want to know the arc length. Oh, and this function will be called x equals, I don't know, g of y, you know, like x equals y cubed plus y, you know, that kind of look. And if you want to get the arc length, it also has a formula. Anybody want to have a crack at what the formula would look like based on what you see up here?
Are we going to use the derivative of f of y?
Yeah, I'm calling it g of y, but
y.
f of y, yeah. What would the limits of integration be then? Where should I start and finish with this question?
C to d.
Yeah. One plus, I'm calling it g of y just to make it a little bit different, right? The derivative squared dy. Remember a way back, haven't we done some integrations where you integrate in the y direction rather than the x direction, right? Actually, haven't we done integrate with t's, with u's, with thetas, and with x's? So what the heck, can't you integrate with any letter of the alphabet you like, right? So you can do it with your y's. Right, now, let's show you some examples. Let's start off with the first one, which is going to be a straight line. Let's see if I can find a straight line that make my life too hard. I'll just pick one. Suppose you have the straight line y equals 2x plus 1, and you want to get the arc length from x equals 1 to x equals 3. Right? So if I wanted to see what it looks like, it would be there's 1, there's 3. I'm basically just trying to find out what that distance there is. Right, that little green guy. You agree you could probably do that lots of other ways and not use this formula, but it's a good starting point. So the function is 2x plus 1. Its derivative is 2, and 1 plus the derivative squared is 1 plus 2 squared equals 5. This is kind of the way I do all these questions. I find this bit inside the square root first. And then once I've got to that point, I do the integral from, in this case, 1 to 2, the square root of this guy. Oh, don't need that room. Dx. Would you agree that's a very simple integral? Don't overthink this. That's a huge gap. You don't need that. What is the integral, antiderivative if you prefer that name, of the square root of 5? And don't overthink. The square root of 5. Well, if it was 2, the answer would be 2x. If it was a half, the answer would be a half x. It's the square root of 5.
The square root of 5x.
Thank you. You know, I'm getting old every day. So you got to be faster. Let's go. So square root of 5 times 2. Take away square root of 5 times 1. Well, 2 of them, take away 1 of them. Oh, the final answer is the square root of 5. So that was a nice, simple, nothing really weird going on, but it gets us into the swing of things. Let's up the ante and pick this fella. This is a version equation 5. Won't be quite yours, but it will be similar. And the function that we're going to be finding the arc length for and the x's are going to be from 0 to 1. So my usual technique is to find the derivative, to square it and add 1. In this case here, you're going to do the power rule. So I'm going to multiply by the power and reduce it by 1. So 8 times that gets me 12. And then reduce it by 1, you get a half. Then I'm going to do 1 plus the derivative squared. So it's going to be 1 plus this guy. Actually, while I'm at it, let's call him the square root of x. And so you're going to get that this fella is 1 plus 144x. Do you notice it's 144x and not 12x? Because 12 gets squared and the square root of x gets squared. So the arc length is going to be the integral from start to finish. The square root of this guy. So that's what we need to find, and we're done. You could do a U sub. If you want to do a U sub, there's nothing wrong with that. That would be the U sub you should use. But it's not the only way to do it. If ever I see a square root and there's a linear term inside, like here, then I'm going to use the linear shortcut method. And what that essentially does is that this thing is going to be thought of as that. And now I'm going to add 1 to the power. 3/2. I'm going to divide by the new power, 2/3. And then the linear shortcut method uses this 144x. If this was 1 plus 2x, I'd multiply by 1/2. If it was 1 plus 10x, I'd multiply by 1/10. It's 1 plus 144x, so I'm going to multiply by 1 over 144. And then we can evaluate this at 0 and at 1. And I'm going to do some tidying up here before I even bother to plug in these fellas. That and that can cancel a little bit. And you're left with 72 on the bottom. So what's that? 3 times 72 is 216. So you get 1 over 216. And this fella is going to be the square root of that guy cubed. And the reason I'm taking this 3/2 and turning it into this is that we need exact values. And we don't want 17 to the power of 3/4 or weird things like that, because that's not really the way answers should be written. So, yeah, let's pull that out. Someone suggested last time. If you plug in 1, you'll get the square root of 145 cubed. And if you plug in 0, you get the square root of 1 cubed. And this is a ridiculously ugly answer, but it is correct as well. It's this guy. If you want to simplify this fella, you can. And that's your answer. Now, you may get lucky in WebAssign and you might get some nice numbers where these things come out pretty, but not the one I got. We're getting close to the point where I warned you earlier on today, where your head is going to hurt. That one's messy, but that isn't anywhere near as messy as this one. So the next question I'm going to do is like question 7. And the function is that guy. And we're going to find the arc length from 1 to 2 of this function. Let's start off with what might not seem obvious, but is actually helpful. I'm going to rewrite this term as 1/4 x to the negative 1. It's a common mistake that some people think, hopefully you're not one of them, that this is that. Now, I can understand why they think that. Don't they think the 4 and the x are like nailed together? And so if the x moves, the 4 just goes with it. But technically speaking, if you cover up that x, I should do it this way. If you cover up that x, do you see there's a quarter? Right. It's its own thing. So that's why that's there. The second reason I did that is more important than just, you know, it looks pretty. If I'm going to differentiate this, don't I need to use the power rule? In which case this has to be called x to the negative 1. So let's see what we get then. Its derivative. Multiply by the power and reduce it by 1. Multiply by the power and reduce it by 1. Now, 1 plus the derivative squared, right? This bit. 1 plus this guy squared. And I've written it down that way because that's essentially what squaring is, right? The thing times itself. And I'm going to have to do FOIL. Told you there's some stuff here that you haven't done for a while. Now, x squared times x squared, the first one in the list. So let me do that. You get x to the 4. So that's what F got you. If you go and do the outsides, that's a little bit weird. I've got an x squared, and it's going to be multiplied by negative 1/4 x to the negative 2. When you multiply these together, something really strange happens. Does anyone have a shot at what this becomes?
Negative 1/4.
Nailed it, exactly. Oh, if you want to know why, if you basically you're multiplying 3 things together, right? And all I'm doing is I'm putting them in a different order. And do you know if you take this guy times himself, don't you get x to the 0? And that's 1. And that's negative 1/4. Or if you prefer, x squared times 1 over x squared gets you 1, but it's the same thing. So negative 1/4. And that's the O. If you do the inside, you also get negative 1/4. And if you finish with the last guys, these two, you get negative 1/4 this guy times negative 1/4 the same guy. So 2 negatives make a positive. 2 1/4s together get you 16. And 2 negative 2s get you a negative 4. And that's the L. Now, if you combine these, you have an x to the 4. The number in these two guys gives you plus a half. And at the end, you've got 1/16 x to negative 4. Now, there are quite a few questions in the homework that end up looking weird like this. If you ever see 3 terms, right, 1, 2, 3, you are looking at a perfect square. Now, the normal kind of perfect squares are probably the ones you're not going to see. A normal perfect square would be things like x squared plus 6x plus 9. And that ends up being a perfect square, which is just our way of saying the 2 factors are the same. Now, if it was that, I would expect you to notice that. I'm not so sure you notice that that's a perfect square. So let me show you how you get it. X to the 4. Take the square root of that term, half its power. See this guy here? Take its square root. What about the guy in the middle? Don't worry about him. He'll sort himself out if you did it right. This fella is positive 1/4 x to the negative 2. And if you take that thing and you square it out like I did here, can you trust me that that's what you get? It works. So when you see 3 terms Square root of the first, square root of the last, that's your perfect square. So I can now do the arc length. It's going to be the integral from 1 to 2. The square root of this guy. And this is where it gets kind of interesting. Isn't the square root of something squared cancels each other out and the square root disappears with the square? And what you're left with is the integral from 1 to 2 of x squared plus 1/4 x to negative 2. Get off through that guy. Which is really good news. Would you agree you do not want to find integrals of square roots? Don't they always end badly? Right? They either are impossible to do or horrendously difficult to do typically, right? But if you have a square root disappear on you, that's good news, because although that might look ugly to you, isn't it just a power rule? So let's see what we get. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Evaluate it at x equals 1 to x equals 2. Do a little bit of style points, but not much. Okay, if you plug in 2, you get 8/3. If you plug in 2, you get an 1/8. Take away, if you plug in 1, you get 1/3. If you plug in 1, you get 1/4. And that's what calculators are for. So let's see what we get. 8/3. Subtract 1/8. Subtract another 1/3. And subtract and negative is adding. Add a 1/4 then. Hit the math button. Option 1, go for it. 59/24. You're finished. Would you agree that's some heavy duty algebra? All sorts of things going on, lots of places where you could, if you're not careful, could lose track. Any problems with that? Can I move on to another example? If you want to, I got a nod, that's good for me. Try to find one that's, yeah, this one. This is a version of question 11. And this is x squared equals y take away 4 cubed. And we're finding the arc length from 1,5 to 2713. Now, the first thing I'm going to do with this question is find out what x is. That's basically the guy I've been calling g of y. So do you see it's going to be this second situation? This integral is going to be a dy guy. Now, I also need to know what the start and finish value of y is. And it's not 1 and 27. Isn't it 5 and 13? Are you comfortable with where the y 5 to 13 is coming from? So far, so good. Right, let's get the process. We have a function that looks like that guy. And we are going to differentiate this guy with respect to y. In mathematics, you can use that notation if you like. If this bugs you too much, because for some people it's just too much to take in, couldn't I just rewrite this guy as g of y? Do you feel a little bit more comfortable now about the derivative? So sometimes you just have to write it down in a way that makes you feel good. So I'm going to stick to that now. So multiply by the power and reduce the power by 1. 1 plus the derivative squared becomes 1 plus this guy squared. Now, if you've got terms that are all multiplied or divided squared, you could just do it to each one separately. So that 3 becomes 9, that 2 on the bottom becomes 4, and this half power just becomes that guy. And now I have 1 plus 9 quarters y, take away 9, which becomes 9 quarters y, take away 8. So our arc length is going to be the integral from 5 to 13, the square root of this guy, dy. I'm not going to finish this question, but I will start it for you. Do you know I could do this question 2 ways? Couldn't I do it as a linear shortcut method? But that might be a little bit too much in some for some people. So you might choose in this particular instance to just do a U sub. But you will get the right answer no matter what method you do. We go with that one. Just wanted to show you an x equals function of y. Don't want to get into too much details. Let's look at a weird one. God, there's enough weird ones going on, but I want to find another weird one. Ah, there it is. I knew it was around somewhere. Now, I'm going to take this question about 3/4 of the way through, so you've got something to work with. If you want to differentiate the natural log of secant x, we call that a chain rule. Remember Calc 1 chain rule? So if you differentiate a log, you get 1 over the thing, followed by the derivative of secant x. Have I got my guy handy? Yeah, I do. Go for a volunteer. I'd like you to get it right, but at least have a shot at it. What's the derivative of secant x? Maybe you've got it written somewhere.
Secant x, tan x.
Ah, well done. So you did have it written somewhere, or you just have a good memory. Oh, wait a minute. Won't they cancel and all you're left with is tan x? Isn't that a really nice answer? Could have been a lot worse. Now I'm going to do 1 plus the derivative squared. In this case, it's simply just going to be 1 plus tan squared. And then you might get caught out. Is there any better way, simpler way, to write 1 plus tan squared?
Secant squared.
Yes. Which means that we are in a good place, because the arc length is going to be from 0 to pi upon 4. The square root of this guy and isn't secant squared a nice square root? Now, I know someone contacted me, no, actually a couple of people contacted me about a homework question where you were left with this guy. And I said something along the lines of, well, you know, sometimes you get an integral that you don't memorize and you go and you look it up and then you stick it in your little list. Has anybody got that guy handy? Because I've got it under this piece of paper. But does anybody here, for whatever reason, remember what the integral of secant x is? And it's not secant tan, which is a sensible guess, but it's not. I'm about to show you it if you can't remember it. Okay, go for it. It's the natural log of the secant of x plus the tan of x. And at this point, you're just going to plug pi upon 4s in and zeros in, and you are going to come up with the exact value. So you can't just say, I don't know, that the secant of pi upon 4 is 1.414, which it is, by the way. You're not allowed to do that. You must tell me as root 2, for instance, would be that one. So exact values in. Any questions about that? How you would kind of plug in some numbers and finish it yourself? Okay. Then we are ready for the last piece of this film. I would go in. We're doing really good. Hopefully I'm not going too fast. There is a bunch of questions at the beginning of the homework where it says set up, but do not evaluate. So all you're going to do is set up the integral, but not actually do any more than that. So these are kind of quick. So this is, well, let's pick one. This is an example question 2. So setting up an integral is not the same thing as doing all the algebra, right? All the way to the end. They just want you to set out what the integral would look like. Right, now in this case here, I need to find the derivative. And that's pretty much all I need to do. Oh, would you look at that? Isn't that an ugly power rule, product rule? And the product rule is f dash g plus f of g dashed. And so you're going to get 1 times e to the power of x to the 6 plus x. And I am now going to do a deliberate mistake. Oh, the derivative of e to the power of e to the x to the power of 6. It's hard to say that. E to the power of x to the 6 isn't just e x to the 6. Isn't it a chain rule? What's missing? If you were only being asked to do that now, I've just written down that that's what the derivative is. And I'm saying that's not the whole picture, is it? Don't you have to multiply by something? So what's missing?
You would do the derivative of x to the 6, which is 6x to the 5.
Agreed. And then I would make this look pretty. So I'd get this guy with this guy. Okay. And then essentially, wouldn't the answer be the integral from 0 to 6, the square root of 1 plus all of this? Now, do you notice that they don't want you to square this and multiply it out and collect like terms? That's actually as far as you need to go. So it's not more than find the derivative and stick it in here, right? So when you're doing your question, it's going to look like that. And see where these dots are? That's where you put the derivative of your function. So you don't need to FOIL it out. You don't need to collect like terms. Really, all you need to do is do the derivative. And of course, make sure that you write down the limits of integration for your question. Are we comfortable with that question? Do you want to see another one? Or are you good?
Do it.
We're good? Okay. I think that's what I heard. I hope it's what I heard. Right. So let's just keep going. This is good stuff. So, oh, we need a joke. We need a few minutes just to give our brains a settling down period. Did I do my Arkansas joke? Because evidently I did it with Mother Talk too. You have not heard my Arkansas jokes? Katie, do you want to hear my Arkansas joke?
Sure.
Not very convincing. Okay, Ryan, do you want to hear it? Sarah, do you want to hear it? Not sure. Sarah, whoever is with you, they have to pay me money because I only get paid by you. So whoever that one is, they owe us money. So I'm just telling you that right now. My rate is $14 an hour. So that's about $28 by the end of tonight. Okay, here goes. What is the difference between a divorce and a tornado in Arkansas?
Let's hear.
There is no difference. Both ways, somebody still loses a trailer. Okay. Do you know that the toothbrush was invented in Arkansas? They know that the toothbrush was invented in Arkansas because if the toothbrush had been invented in any of the other states, it would have been called the teeth brush. Oh, right. Skylar got that one. Oh, Taylor liked that one. What else I got? What do you call 26 un-Arkansonians in the same room? A full set of teeth. Oh God, poor Mark's crying. That's good. Has anybody, we've got a couple more minutes. We deserve a few more minutes. Has anybody got some really bad corny jokes for me? Because I need some too. Nobody yet?
I don't have any.
Did I tell you the joke about the Scotsman, the Polish, and the American guy trying to get into the Olympics? Well, they were over in, the opening ceremony, trying to get into, they wanted to do it, and they had no chance. The tickets were sold years ago. It was sold out. Not a chance. Security guards everywhere. They couldn't sneak in. And they're sitting kind of depressed, trying to figure out how they were going to sneak in. And they were in this building site, in some building right next to, the main place. And the American looks around and he says, "Hey, I've got an idea. We can sneak in." And the other two says, "How?" He said, "Just do what I do and you'll be fine." So the American picks up a scaffolding pole and he puts it on his shoulder. And he walks over to one of the side doors and a security guard there. And he walks up to him and he goes, "American athlete, pole vaulter." The guy looks at him and thinks, "Aye, okay, in you go." So the Scotsman said, "That's great, I'm going to do that." And he looks around and he finds a big hammer. He puts it on his shoulder. And he goes down and goes up to the same guy and walks up to him and goes, "Scottish athlete, hammer thrower." And the guy looks at him and says, "Aye, okay, in you go." So the Polish guy looks around and he finally finds a roll of barbed wire. A roll of barbed wire, puts on his shoulder. Walks over to the side and he goes up to the guy and he goes, "Polish athlete, fencing." Oh, come on, Ryan, that's good. Ben thinks it's good. Katie thinks it's good. Sarah, I'm getting nothing from you. I'm dying here. That was a good joke. No? Yeah, whatever. Right. Well, let's get started on the next section since time is valuable to all of us.
Some in
Oh,
the want.
we got some. A small psychic escaped prison. There was a small medium at large. Oh, cool. Thank you. Is there any more there? What dating website do hillbillies use? Oh God, no, I'm not going that one. No, you'll have to read that one. I'm pushing that one a little bit. Okay, everyone, if you hold on, I'll move on to our next session, which is surface area. And darn it, yeah, getting confused here. Just going to exit this for a few seconds. I need to get something up and running. Wasn't quite expecting this to go so smoothly, which is nice. I like that when it happens. They normally have a really good picture, which is what I'm trying to show you, if I can. Oh God, it's hopeless. It's useless.
Professor,
Yes,
will arc length always be a positive value?
yes. It
Okay.
can't be negative because it's a physical length rather than a, you know, a like net area kind of situation. So it's a little bit right. Well, I can't show you the, well, I could show you the picture, but they're pointless. They're just as ugly as the ones I'm going to do. So I'm just writing down the general formula right now. So I keep the lettering the same way that they do. And I'll try my best to do my rendition of a 3D shape. So let's get started. Got myself set up now. You're going to think that we've returned to the dreaded volumes of revolution question, because in a lot of ways, these questions do look similar. I want you to imagine that we have a curve, y equals f of x. And it starts at A and it finishes at B. And we're just going to, right now today, focus on rotating about the x-axis. Now, if I, 1, 2, 1, 2, it's about there. It's about there. Kind of goes something. That's not too bad. Can you imagine what this shape would look like? Wouldn't it look a bit like a bell? Right? Now, we're not going to find the volume of that bell. We've done that. That was a way back 3 weeks ago, whatever. We are going to find what's called the surface area of that bell. And the surface area, if I can try and draw this bell again, kind of a slightly different orientation. This curved piece here, right, that goes right round the bell, that's called the surface area. It doesn't include the circles at the start and finish, right? Just the middle bit, right? And we are going to find that surface area. And here is your magic formula for doing it. Now, if you look at this formula and you go back and look at other formulas, you'll see that it's got a bit of A and a bit of B in it. Do you recognize this piece of the formula? Isn't that arc length? Isn't the 2 pi f of x very similar to the volume guy, right? Remember doing the volume guy. So it's like a Frankenstein formula, made a bit of rotation and a bit of arc length. So as long as you give me f of x and you give me a start and a finish value, then we are good to go as far as calculating exact areas on the curves. So this is what, example question 2 from the homework. The function is very nice. The start and finish values of x, nothing spectacular there. In order to get this integral, right, the surface area, we're going to have to do the integral from a to b, 2 pi f of x, the square root of 1 plus the derivative of this guy squared. Now, because that particular expression was so simple, do you see I managed to do that in my head without too much work? Now I've got 0 to 2. I like to pull out the 2 pi just to get it out the road. And now we've got this fella, 9x to the 4, essentially. And that's the guy that we need to integrate. And there is only 2 guys inside the square root. So it's not a perfect square. There are going to be some situations where there's 3 guys inside the square root. If there's 3 guys inside the square root, won't it be a perfect square? Right? And we'll show you the trick when that happens. But when there's 2 guys, it ain't. How am I going to integrate this? What technique shall I use?
What was the question again?
What method shall I use to integrate this?
U sub.
U
Yeah.
sub.
Nailed it. U subs. Would it be pretty obvious that the U sub is everybody inside the square root? Do you agree? Well, let's see what that looks like then. If you differentiate with respect to x, you get a rather ugly 36x cubed. If you do the crossover, you get 36x cubed dx. And if you isolate the dx, which is typically the last thing you do in U subs, you get that. So it's 2 pi, the integral. I always lose the limits here. We have an x cubed, a square root of u, a 1 over 36x cubed, and a du. The x cubed cancel, and I get 1 over 36, the square root of u, du. You know, I could probably pull that 136 out as well while I'm at it. And if I do that, are you happy with that? I'm just trying to make the integration as simple as I can get away with, right? Just pull out anything that's not a square root. Now, to integrate this guy, as we've done 100 times before, you have to turn it into a half power. And then you can do add 1 to the power and divide by the new power. And that in turn gets returned. Well, 3 halves is actually 1 plus 9x to the 4, right? So it's the square root of the guy, right? All cubed. And then you can evaluate it at 0 and at 2. We've got this guy and this guy. This is going to do a bit of cancelling. You're going to get pi over 27 now when you multiply them together. When you plug in 2, you get 2, 4, 8, 16. Good grief. 9 times 16. You get 145. So it's the square root of 145 cubed. Take away, take away cube root of 1. Take away 1. And so there's your answer. Not very pretty. But the surface area that you would get if you rotated x cubed from 0 to 2, right, the curved bit in the middle, this bit that might look something like that perhaps, is this answer here. It's not that uncommon when you do these questions that you will end up doing a U sub. They happen now and again. It's not that uncommon. Are we good with that one? I mean, it's only the first one, but you get. Okay. Let's do a scary one. Didn't take long to get to the scary ones. Here is question 3, or at least one like it. This one's too much going on for me to plug it right in. So I'm going to find the derivative. And actually, before I find the derivative, let's write it like that. Now I can find the derivative. Multiply by the power and reduce the power by 1. Is there anything missing from that derivative? I multiply by the power, which is a half. I reduce the power by 1, so that's negative a half. Is there anything missing?
Multiply by the derivative of f minus x.
So multiply by negative 1, right? So the only thing that's missing was a little negative. Now, 1 plus the derivative squared, so I'm going to do that separately. So this is very like what you would do with arc length, isn't it? It's the same kind of stuff. So you're getting extra practice at doing this. That's going to be 1 plus this fella squared. Okay. If you take negative a half and square it, you get positive a quarter. And something really nice happens. If you take this guy here to the power of negative a half and you square it, don't you just get this guy here to the power of negative 1? Are we good? Now, if you do some style points on it, it looks like that. And although it might not seem something that you need to worry about, it is something that you need to worry about. Whatever goes inside that square root has to be made as nice as possible. You can't leave 2 fractions there. If it's a perfect square, for instance, make it a perfect square, right? You've got to make it as good as it can be, which means you're now going to have to bring in a trick that I don't know how long ago you've done it, but I've got to add these 2 things together. And the only way you can add 2 fractions together is by making sure that they have the same common denominator. So do you see that I've rewritten 1 as this guy? So it's got the same common denominator as this guy. That gets me, well, if I multiply it out, 28 take away 4x plus 1 over 4 lots of 7 take away x. That's going to get me 29 take away 4x over 4 lots of 7 minus x. And that's as good as that's ever going to get. I don't think I could do much to it that would be worthwhile, but I'm going to check. And I have found something that I can do that's worthwhile. Any idea what you could do to the numerator, the guy in the top? $92 take away 4x. Anything come to mind that you could do with the top?
Should that be 29?
Oh, shooting space. In which case we're finished. Right. Well, back to my question. Not my question, this question. It's going to be the integral from 1 to 7. 2 pi f of x, which is this guy, times the square root of 29 take away 4x all over 4 lots of 7 minus x dx. Now, superficially, when I look at that integral, my first reaction is, oh, we are in serious trouble. They're never going to get anything out of this. This is ugly. What's going on? But stick with it. This is going to get nicer. And it's going to be doable. Right, I'm going to do my little tricky pulling out the 2 pi because it just bugs me. Now, do you know if you've got a square root of fraction, you are allowed to separate them out as 2 distinct square roots. So that would be my first, tackle of this issue. And then I'm noticing that there's a guy on the bottom here, him, who can be separated out as the square root of 4 and the square root of this. Well, the square root of 4 is 2, and the other guy is this. Can you see something nice happening there? Isn't there something kind of cool? You see these 2 cancelling? So bring this 2 out and you get a pi. We are now looking at that fella, right? That guy is doable, isn't he? And I'm going to do the same thing I did last time. If you think it's too much to handle, do a U-sub. And if you do a U-sub on that, you'll get an answer. Sneaky? Kind of cool. Any questions? Are we good? Last chance for this one. We're good. Okay. This is probably going to be the last question today. And we still have 23 minutes to go. So you might think, how on earth is that going to happen? Well, wait till you see the function. I can tell you right now that, see this bit inside the square root? It's going to be a perfect square. And how do I know that? Well, I've seen enough questions in arc length and in surface area that whenever I see 2 fractions like this, it almost always ends up being a perfect square. So, if you get an x to the 4 over 8 plus a 1 over 2x squared, that kind of one guy, second guy thing, they just the math of it, they tend to come out as perfect squares. So I'm going to rewrite this guy as 1/6x cubed, 1/2 x to the -1. Then I'm going to differentiate him, and I get a 1/2 x cubed minus 1/2 x to the -2. And then I'm going to do 1 plus the derivative squared. And that's going to be 1 plus, nobody noticed. There, fixed it. That guy, take away that guy, squared. And if you FOIL this guy out, you will get this fella, this fella, this fella, and that fella. And then you tidy it up. You got this guy, you got this guy, and you got this guy. It's very deja vu, isn't it? It's very like, what about the second, third question we did today? Do you see 3 terms? Isn't that the signal for a perfect square? And you look at the first guy and you look at the last guy. And if you take the square root of them, you should be good to go. So that'll get me a half, and that'll get me x squared, right? And this guy will get me a half, and this guy will get me a -2. And you can trust me, but multiply it out and it works. Perfect square. Are we good so far? So I got my little formula. It's going to be the integral from 1/2 to 1. Actually, I'll write the formula down, that way I can hide it and we can plug the pieces in. In our question then, its surface area is from 1/2 to 1. Stick the 2 pi out there. F of x is x cubed over 6 plus 1 over 2x times the square root of all of this looks like I'm running short of ink. So let's see what the surface looks like. 2 pi 1/2 to 1 1/6 x cubed plus 1/2 x to -1. Just rewrote that slightly differently. And these cancel out and you get this guy. Ugly times ugly. But isn't it still FOIL? It's still FOIL. You're just going to have to deal with the fact that it's not x times x and x times 3. But apart from that, it's still FOIL. So here's my F coming up. If you multiply 1/6 x cubed with 1/2 x squared, you'll get 1/12 x to the power of 5. If you do the outside, which is these two guys, you get, well, maybe I should do it over here. You're going to get 1/6 x cubed multiplied by 1/2 x to the -2. That's going to get me 1/12. But what power of x do you get when you multiply an x cubed with an x to the -2?
Just 1.
Yeah. So that guy there is going to be a plus 1/12 x to the 1. And that's the guy we're calling O. Now, if we do the inside, it's very similar, but you get a 1/4 x. And if you do the last ones, a bit messier, but a half times a half gets you 1/4. And a -1 multiplied by -2 gets you x to -3. And we have just done a really messy FOIL. I should tidy it up as best I can. So I have this fella. I have 1/12 of x and 1/4 of x, which adds together eventually, you get 1/3 of x. Okay, where do we go now? Well, isn't this just power rules? So add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. add 1 to the power, divide by the new power. Evaluate at x equals 1/2, x equals 1, almost there. That's okay. That's okay. If you want exact values, you better write this guy that way. So that was just a little cosmetic thing. Okay, so I get 2 pi. If you plug in 1, you get that fraction. If you plug in 1, you get that fraction. If you plug in 1, you get that fraction. Take away. Oh, yeah. Take away a really small number. That's going to be 1/2 to the power of 6. So I'm just going to write down what it is, because I'm going to have to figure out if I can even do that on my calculator. Plus 1/6 squared. Take away 1/8 squared. Let me check something out here. I'm going to just check out the answer. And you are going to trust me, but you get 263/256 pi. So evidently, all of this horrible mess, including that too, ends up simplifying down to that. I don't have a problem with this side. I can certainly do that, but can you imagine 1/72, 1/2 to the power of 6? Can you imagine that's going to be some ridiculously ugly, very small fraction? But nonetheless, it looks like it, you know, they all play well together and you get a reasonably nice looking fraction.